Hi, my name is Silvia Casacuberta, and I will be talking about our paper, How Global Calibration Strengthens Multiaccuracy. This is joint work with Parikshit Gopalan, Varun Kanade, and Omer Reingold. In our work, we discuss what we think are really interesting relationships between notions in fairness, in complexity, and in learning. Specifically, we will be talking about definitions in multi-group fairness, in algorithmic fairness, the hardcore lemma in hardness amplification, and agnostic learning in learning theory. In all of these three worlds, we will see how calibration plays a really key role, adding a lot of power to these notions, in all three cases in a really modular way. I will start by defining the required notions in the fairness, learning, and complexity world. Then we'll see the power that calibration gives us in the learning theory realm, and then we will see the power that calibration gives us in the complexity theory realm. Let's start with the multi-group fairness notions. As we all know, algorithms are being used in all spheres of society to decide who to give a loan or which student is more likely to need an extra teacher. There's a lot of concerns that there's discrimination against individuals or groups when these algorithms are being used. So a typical problem is that you might have built a predictor P that has good probabilities. We think good accuracy. We think of this predictor as giving us individual probabilities in the case of risk prediction. But is this enough to have good global accuracy? The issue is that you might then condition in a minority group and have really bad accuracy there. So a solution is to require more stringent notions of accuracy by asking that the predictor be accurate in many subgroups of the domain simultaneously. This led to the proposal of the notion of multi-accuracy by Everett Johnson, Kim Reingold, and Rothblum in 2018, where we want accuracy with respect to an entire collection of groups C. So we have this distribution D on the domain X that we think of individuals. We have a collection C of protected groups. P star represents the ground truth predictor of these individual probabilities, and P is a predictor that we are building. And we say that P is multi-accurate with respect to C and epsilon. If for every C and C, this boxed condition holds. What this means is that inside of each of the subgroups marked by the collection C, the expected value of P star is approximately equal to the expected value of our predictor P. And this holds for every C in the collection. That is, we require accuracy on expectation with respect to all of these Cs. And I like to think of this as sort of a Turing test, where we're saying that the distinguishers in C cannot distinguish between the true labels and the predictions in this accuracy and expectation sense. The notion, a central notion in our paper is that of global calibration. This is the typical notion. So it says that a predictor EP is calibrated. It's if when we look at the subset of values where we, the predictor P, predicts V, the expected value of the true probabilities P star on that level set is approximately V. In a way, this is that the probabilities are meaningful in that they mean what they say. And we also use Y for the Boolean label. So think of Y as generated from a Bernoulli of parameter P star. So Y is Boolean. We won't go into a formal definition, but another more stringent notion than calibration is that of multi-calibration, which is stronger than multi-accuracy. And multi-calibration requires calibration to hold not just globally, but within every C in this collection C of subgroups of the domain. There's been an explosion of multi-group fairness notions in the past few years and many, many applications of these really useful notions in all sorts of domains. And in our work, we focus on the learning and complexity aspects. We'll briefly review how the multi-accuracy algorithm works. Essentially, we initialize a predictor P, and then we start the following iterative procedure. We say, while there is a C in C that witnesses a violation of this multi-accuracy condition, then we update the predictor P using this C. And you can think of this as a gradient step. You can show that it's going to take no more than 1 over epsilon squared many updates until this process terminates, and therefore we get a multi-accurate predictor. And so this is an efficient procedure. And in order to find a weakness in C that sees this violation of multi-accuracy, we use the learning theoretic object of a weak agnostic learner. Because notice that finding a violation of the multi-accuracy condition corresponds to finding correlation between some C and C and the residual quantity P star minus P. What is weak agnostic learning? It's parameterized by 2 parameters, alpha and beta, and we say that an alpha beta weak agnostic learner for a concept class C promises the following. If there is some concept in C that has correlation at least alpha with the labels, then we get a hypothesis H that has at least correlation beta with the label. So think of beta as smaller than alpha. And you can see the formal definition of correlation below in the slide, where we make it be in the -1, 1 range. And so that's why we shift the Boolean label from y to 2y minus 1. And the concepts C are in -1, 1. And the strong agnostic learning notion says that we being the hypothesis H, gets correlation basically as good as the best in C. So it's a stronger notion. We have seen briefly the algorithm for multi-accuracy, and it takes 1/epsilon² iterations to obtain a multi-accurate predictor. A similar algorithm works for the stronger notion of multi-calibration, in that case with 1/epsilon⁶. And in both cases, we use the weak agnostic learner as the main primitive. In the case of multi-calibration, the original paper shows that the equivalence holds both ways. So if C is multi-calibrated, it is also agnostically learnable, and with the same predictor. So if P is multi-calibrated, the same predictor P is a strong agnostic learner. But we don't know what's happening in the other direction in the case of multi-accuracy. And this is the first main question that we're going to study in our paper. And before we do that, I'm going to give you the definition for the complexity theory part. So the hardcore lemma comes from a connection between the complexity theoretic regularity lemma and the theorem saying that we can build multi-accurate predictors. So we just gave an algorithm to build multi-accurate predictors. Turns out that this is exactly the complexity theoretic regularity lemma of Trevisan, Tulsiani, and Vadan that was given in the early 2000s, preceding all of the literature on multi-group fairness framework. In their context, what we have been calling multi-accuracy, they called it C epsilon indistinguishability. And the fact that we can build P in this iterative procedure using distinguishers from C, in the complexity theoretic world, we say that we can compute P with an oracle size circuit with oracle gates to C that is not too big. And so specifically, we'll be saying that P belongs to the class CQ. So P has low complexity with respect to C, because we can think of P as a linear combination of 1/epsilon² many C's because of these gradient steps that we take, updating the P with functions from C, where Q is of the order 1/epsilon². And you can see the diagram at the right bottom of the slide. The other really exciting thing of the regularity lemma is that it has really important implications in many different domains, in graph theory, in complexity theory, cryptography, and so on. And in our paper, we focus on the complexity theory connection, specifically to Pagliacci's hardcore lemma. Pagliacci's hardcore lemma is a result from the 90s, first shown by Russell and Pagliaccio and then improved by Hollenstein, that sits in the realm of hardness amplification. So in a nutshell, it tells us how we can go from a function that is somewhat hard to compute to a function that's very hard to compute. Specifically, we start with a Boolean function g that is assumed to be hard with respect to this class CQ. What does it mean to be delta hard? It means that for every C in C, there's always at least a delta fraction of the domain on which C fails to compute G, meaning they do not have the same outcome. Everyone is Boolean here, so that's what we mean by they're not equal. And so C errs to compute G on at least a delta fraction of the domain. And this is true for every C in CQ. So this is an assumption on G. This is what we mean by saying it's somewhat hard to compute. Then Pagliaccio showed that this implies that there exists a fixed set H in the domain, that's called the hardcore set, inside of which the function G is maximally unpredictable with respect to C. Meaning that for every C in C, C errs to compute G on at least half a minus epsilon fraction of the domain. So basically, C cannot guess G better than a random coin flip. So G is very hard to compute. And this is something that is desirable in the realm of cryptography, and that's also how the hardcore lemma came about, so that we can obtain hardcore predicates. Moreover, we need to say something about the density of H, and turns out that the optimal size that the hardcore set H could have is 2 delta. Okay. Originally, Pagliaccio showed how to get delta density, and it took 10 years for Hollenstein to show that we can obtain the optimal 2 delta density. In the rest of the talk, we will use the measure version of the hardcore lemma, in which instead of saying that we have a fixed hardcore set of the domain on which G is very hard to compute, we say that there exists a measure, which is a function from x to 0, 1, such that when we sample according to this measure, G is very hard to predict. And the corresponding notion of density translated into measures is the one that you see at the bottom left of the screen, which is the expected value of the measure under the initial distribution D. Okay. Now, Travis and Tulsiani and Vadan showed that we can prove the Harker lemma from the regularity lemma. And the key idea is to define the measure that we call mu TTV using what we would say the multi-accurate predictor P. So from the initial function G, we build a multi-accurate predictor P, and then we construct the measure in the sense that you see in the middle of the screen, so just G minus P. And then you show that this is a Harker measure and that it has density delta. And importantly, they only get density delta, which is suboptimal. And essentially, the proof of hardness and density is separate, and the former follows from the indistinguishability guarantees of multiaccuracy, and the latter follows from the fact that G is delta hard. So to recap, from the multi-group fairness framework, we have these notions of multiaccuracy and multi-calibration. Multi-accuracy turns out to be equivalent to the notion of C indistinguishability from complexity theory. From it, we can prove the Harker lemma with density delta, as shown as Travis and Tulsiani and Vadan. In previous work by Casacuberta, Dwork, and Vadan, we showed that from multi-calibration, we could get a stronger form of the Harker lemma, which would then imply the Harker lemma, the original one, with density 2 delta. So multi-calibration does allow us to get the optimal 2 delta size of the Harker set. We saw how we can construct these notions from weak agnostic learning. And so the two glaring questions, one we mentioned it before, is does multi-accuracy imply weak agnostic learning? The other one is what multi-group fairness notion corresponds to the Harker lemma with density 2 delta, allows us to prove the Harker lemma with density 2 delta. We know that multi-calibration does do that, but can we find a weaker notion in this column that would give us a Harker lemma of density 2 delta? As you might be expecting from the title of our paper, calibration will turn out to play a key role in both of these open questions. I'll start by going into the learning theory results of our paper. I'll go a bit quick in our results, so please feel free to stop in this video and look at the slides. First, what happens when we do not have calibration and we only have multi-accuracy? So I'm tackling this first box question. Turns out that unlike for multi-calibration, we can construct perfectly multi-accurate predictors that are not agnostic learners, not even weak agnostic learners. How do we do that? So consider the strings of n bits on -1 and 1, and we're going to define the class C to be the set of all functions in the first n-1 bits. Okay, P star is whatever it is, and now I say, okay, I make P be whatever P star says, but flipping the nth bit. That's the definition of P. The first claim is that P is perfectly multi-accurate. Why is that? Consider the multilinear expansion of both P star and P. I've just separated the terms that do not depend on the nth bit and the terms that do depend on the nth bit. By definition of P, as P star flipping the nth bit, we can rewrite these two functions. And so when we subtract them in the form that we're going to have in the multi-accuracy condition, the blue term disappears and we only get left with the purple term. So notice that when we write the multi-accuracy expression of C times P star minus P, C and P1 star only depend on the n-1 bits, and xn has expected value 0. And so we get that the multi-accuracy quantity is always 0 until P is perfectly multi-accurate. Next, we'll show that despite the fact that P is perfectly multi-accurate, it is not a weak agnostic learner. In fact, it is also not a weak agnostic learner for any post-processing of the outputs of P. Let's give a concrete P star function now. P star is going to be the majority of the first, the second, and the nth bit of the input string. And so by definition of P is going to be also the majority of the first, second, and the flipped nth bit of the string. So what happens now? Notice that P star and P disagree on half of the 2 to the n inputs, even when conditioned on the value of P. So if we look at the inputs where P is saying 0, you will see that for half the values, in this table, there's meant to be 2 to the n values, right? Because we have all the possible bits from x3 to xn-1. And so conditioned on P being 0, P star and P disagree on half of the values. Conditioning on the values where P is equal to 1, they disagree on half of the values. Therefore, if you do the math, you see that the correlation between the true labels and P, and in fact, any processing of the values of P is 0, which means that P is doing no learning of the labels. This doesn't fully tell us that it's not a weak agnostic learner because we need to check whether someone in C does have correlation with the labels. But it turns out that the dictator function C1 achieves correlation 1/2 with the labels. And therefore, P or any post-processing of its values is not a 1/2 beta weak agnostic learner for any beta. Okay? So without calibration, multi-accuracy alone, a multi-accurate predictor is not necessarily even a weak agnostic learner. So this tells us that this implication is not true, unlike for the case of multi-calibration. What happens when we bring calibration? The key idea, and this really key recurrent idea in our paper, is that calibration allows us to argue about the error of a predictor because we can condition on the level set and then apply the calibration condition. Right, so take this example on this diagram. Look at the level set where the predictor P is saying 0.6. So that's the V level set where V is 0.6. If you're calibrated, we know that, assume perfectly calibrated, we know that 60% of the points in this level set are 1 and the rest are 0. Right? This is what calibration tells us. And so we are able to argue about the error that P is incurring thanks to calibration. So more broadly, if now you condition on every level set and then you average the errors, you'll see that on every level set, we can compute the total error with this V parameter, right? And so the point is that P is learning the labels quite well if it's perfectly calibrated, unless of course V is close to 1/2. Okay, and we'll be using also this balance parameter, B, which is the minimum of V and 1 minus V. And so notice that with this calculation, when we have perfect calibration, the error on the level set is bounded by the 2B, where B is this balance parameter. So we formalize this idea in the paper that a calibrated P learns the labels quite well, unless we're close to 1/2. And so that's why we lower bound the correlation between Y and P by using the distance from P to 1/2. And you can think of 1/2 as a random guessing predictor. And you can also rewrite this random guessing expected value with the balance parameter BP. And here the subscript P just means that we've conditioned on the piece P of the domain. So this is what we get from calibration. Moreover, let's not forget about multi-accuracy, which we also have. If some C in C has correlation with the labels, this gives a certificate that the labels Y are not random, right? And moreover, if P is multi-accurate, it's meant to capture correctly these correlations with the class C. And therefore, if C has some correlation with the labels, this implies, and if P is multi-accurate, that P cannot always predict values close to 1/2. So it pushes this BP balance parameter away from 1/2. And we show this formally in the paper, where you can lower bound the distance from P to 1/2 based on the correlation that C gets with the labels. So this is what we get from multi-accuracy. So when you put these two expressions together, what we get is strong agnostic learning. And so by adding calibration to multi-accuracy, we recover not just weak agnostic learning, but strong agnostic learning. Great, so that tells us that the equivalence here was false in this direction, but when you add calibration, we do get weak agnostic learning. And in the paper, we make some more comments about what would be the corresponding learning notion to multi-accuracy, and we call it restricted weak agnostic learning. Great, lastly, we'll see the power of calibration in the realm of complexity theory. Remember that we were talking about the Harker lemma, which comes from the regularity lemma, which we can view as the multi-accuracy theorem. First, again, we'll start when there's no calibration. We only have multi-accuracy. So I'm talking about this open box that we discussed in the beginning. Recall Impagliazzo's Harker lemma that we defined. And again, we'll be speaking about the measure version of Impagliazzo's Harker lemma. We went briefly through the outline of the proof by Trevisan-Tusian and Vedan. And the key idea, let's focus on the density, because the hardness just follows from the indistinguishability of multi-accuracy. A key idea for the density proof on why this measure has density at least delta is to view the density of the measure as an error function, right? So the definition of density is just what we had before, is the expected value of mu under t. So by this definition of mu, TTV, the density of mu TTV is the expected value of g minus p. But notice that this is exactly the error of the randomized function that outputs 1 with probability p. And this function is in the class CQ. And G is assumed to be delta weakly hard with respect to this class. And therefore, this error must be at least delta. Otherwise, this would contradict the delta weakly hardness of G. Okay. So this is how they get density delta, which is suboptimal. How can we get the optimal 2 delta hardcore set density? Turns out calibration is also the answer. And it's also in a really modular way, in a very similar fashion to what happened in the case of learning. So remember that the key idea is that calibration allows us to argue about the error of the predictor by conditioning on each of the level sets. So let's study the density of this measure by conditioning on the level sets. If you do the calculations, which is similar to what we did in the learning side, this is what you get. You get that the density is 2v, 1 minus v. What's happening here? Notice that this measure is giving weight v to the points that belong to the minority. And here the minority, I mean that if v is 0.6, then we know that there's 40% zeros, 60% ones in perfect calibration. So the zeros are in the minority, whereas the ones are in the majority. And so this measure is giving weight v to the points in the minority and weight 1 minus v to the element in the majority, right? But notice that the base optimal predictor, so the one that would trying to get the least error in this definition of error, would be to output the majority on every level set, the majority value. So if v is 0.6, I would say 1, right? But given that that's base optimal, if we're trying to increase the density, therefore we're trying to increase the error of this predictor, we should be giving more weight to the minority elements, because that's when this predictor is going to pay a price when it's wrong. Right? And so this gives us what we call the mu max measure, which is we should be giving the maximum possible weight, which is 1, because a measure is a function from x to 0, 1, to the points in the minority set, and the rest of the weight to the element in the majority. So this is the intuitive definition of mu max. And if you look at the blue box notion, this is what you get when you put the two cases together of when v is more than a half or less than a half. Okay. So notice that it's a reweighted version of the TTV measure, where we reweight by the maximum of p and 1 minus p on each level set. So we're giving more weight to the level set that have p-value close to a half. What is the density of this measure? Again, we can just compute it. Thanks to calibration, we're able to compute these densities in this more fine-grained way. You'll see that what we get is that the density of the measure is 2 minimum of v1 minus v. How does this compare to the density of TTV? Remember that for TTV, we got 2v1 minus v for the density slash error function. The point is that they're the same thing. And for the mu max measure, we get 2 minimum v1 minus v. Remember the definition of the balance parameter b as just the minimum of v and 1 minus v. And so just by this identity that you can see in this graph, we get that the density of TTV is at least the expected value of this balance parameter across the pieces p, whereas for mu max, it's 2 times the expected value of the balance parameter bp. Again, the predictor that outputs the majority value on every level set has error exactly equal to expected value of BP. But again, this predictor is in the class CQ, and therefore, because G is delta weakly hard, this error has to be at least delta. So when we bring it back to our computed densities, which we computed thanks to calibration, we get that our mu max measure gets the optimal 2 delta density of the hardcore measure. And so this tells us that the weaker notion that gets multi-group fairness notion that is able to get us a hardcore lemma of density 2 delta, because multi-accuracy could not get it, is to add calibration to it. And if you check the paper, we also call it weighted multi-accuracy because we have to reweight the TTV measure. And so that also changes the indistinguishability proof, and we need to account for this reweighting. But it's the same efficiency. Great, so to conclude this talk, we have seen the usefulness of calibration in this very modular way in both in the learning and the complexity realms. In learning, calibration allowed us to relate the correlation of our predictor with the labels to this balance parameter BP. And then when we also added multi-accuracy, and in the case where C has some correlation with the labels, these ensured that the BP, the balance parameter BP, moved away from 1/2, enabling strong learning. In the case of complexity, thanks to calibration, we were able to lower bound the density of our measure mu max, the hardcore measure mu max, by this balance parameter BP. And then if G is delta weakly hard, which is the assumption of the hardcore lemma, this ensured that the balance parameter BP moved towards 1/2, giving us the optimal 2 delta density of the hardcore lemma. So the key takeaways is that calibration adds significant power, both to multi-accuracy in both the learning and complexity realms. And in both cases, it does it in a very modular way. And if you check the proofs in our paper, you'll see that we think are very neat proofs in all of these cases. And calibration allows us to analyze the vector P in a very fine-grained way, and so we can analyze the error by conditioning on its level sets. And a broader point is that calibration, and there's some really amazing concurrent works by Gopalan et al. And Hu and Vedan, where we see a similar phenomenon where calibrated multi-accuracy is able to get us the benefits of multi-calibration with the efficiency of multi-accuracy. There's a lot of richness in all directions, in fairness, complexity, and learning. So thank you very much for listening and looking forward to seeing you in Sydney.